YouTube has let me down. I didn't find the video I was looking for. I wanted to specifically look at conservation of energy for a charge moving through a potential difference, but specifically for a uniform electric field. That's the one that's going to be most interesting to me and for the types of applications we want to talk about. We can look at the electric potential of a point charge, but that's not the direction I want to take this. I want to look at that uniform field. But I first want to make the connection back to things you would have looked at in Physics 1, say a box sliding down a frictionless ramp. We're not going to worry about friction. That's a piece that can be interesting in electrophoresis, and there would be some problems based on that. But let's just look at a box sliding down a ramp if there's no friction. So we have this box here, and let's go from the very top of the hill. From the top of the hill. Now we know we can find the forces acting on this. We could look at the forces, we could resolve it into components, figure out how much of the acceleration vector is pointing down the hill, but the much easier way to do this is by conservation of energy. We can say that the energy initially, the energy at the top, must equal the energy at the bottom, in final. Really, it's a summation of those energies. So the sum of all the energies at the top, sum all at the bottom. But this is going to be a pretty simple case because at the top, if we start at rest, we have no kinetic energy. So at the top, we just have gravitational energy. So I'm going to use, like with forces, a system F sub g, but with energy it's going to be E sub g. You might have used U. I particularly like to use E to remind me it's an energy. So E sub g is gravitational potential energy. So you have all gravitational potential at the top of the hill, and then assuming we get to a height of 0 at the bottom of the hill, then we're going to be all kinetic by the time we get to the bottom of the hill. So this is going to be E sub k. Again, you probably use Ke. I'm going to use this E sub system. So we have, you might hear my phone ringing. That's annoying. I don't know if I'm going to bother cutting that out of the video. You might not have even heard it. So gravitational potential is m times g times h. Kinetic energy, 1/2 mv squared. You can rearrange this equation, you can solve for the velocity, because that's often what we're caring about. How fast is this particle going after it gets down to the bottom of the hill? We don't have to be at the bottom of the hill. We could find starting at some top height and go to some other height. So we could have Eg1 at the top plus Eg2, because maybe you didn't get to the bottom, you're just at some height that's a little bit lower. So mgh1 equals 1/2 mv squared plus mgh2. So then when you bring the mgh2 to the other side, you have mg times h1 minus h2. It's really just the delta h. It's the change in height, which equals 1/2 mv squared. So that's what's important. The velocity depends upon the change in height that the mass goes through within a gravitational field. Now take all of those ideas and apply it to charge. The speed that a charge gains depends on the amount of charge and how much electric potential difference it goes through. With this, it's mass going through a gravitational potential difference. With charge, it's the amount of charge going through an electric potential difference. So let's look at that. I'm most interested in the uniform electric field. So this was the case that we got into in the second example in the worksheet problem, where you have a bunch of positive charges on one side and a bunch of negative charges on the other side. And what we found when you have that is you create a uniform field. Now normally the way we can create that is we can have two metal plates on which we deposit a bunch of positive charge on one and a bunch of negative charge on the other. And then you have this uniform field that points from the left to the right. So we have the electric field vectors point away from positives and towards a negative. But we can also think of going from a high high potential to a low potential. This might be, let's just put some numbers to it to give you a sense. This could be plus 10 volts on this side, and it could be minus 10 volts on this side. It could be 20 volts on this side and 0 on that side. Either way, it's a potential difference of 20 volts. So now to look at the math for this, I'm going to Let me just shift the camera over here a little bit. If I look at the math for this example, I would say, well, what happens if I put a positive charge here? I'm going to put a positive charge. I can put it somewhere in the middle. I'll just put it close to the plate. So we know from thinking in terms of Coulomb's law of repulsions and attractions, this charge will be repelled away from the positive charge, but also be attracted toward the negative charge. But instead of thinking of this in terms of forces, because when you think in terms of forces, it can be a much more challenging picture. If we think of this in terms of conservation of energy, this can actually be quite simple. So we have, well, what is the electric energy, EE, when you're at that side? I always say, that's the sound that a dolphin makes. So electric energy, E sub E, initially is equal to the kinetic energy it gains at the end point, EK, plus whatever its electric energy is at that end point, EE final. Because as long as the potential isn't zero somewhere, now oftentimes we get lucky and the potential will be zero at the end point. We say we go from some high potential 2 kilovolts to 0, and in which case we have 0 potential at the end. But we can also do a case like this where we have positive 10 and negative 10. So now we have to use the idea of, well, what is the electric energy? It turns out to just be the amount of charge times the potential. So the amount of charge Q times the electric potential initially. So V is our term for electric potential, voltage, equals 1/2 mv squared, plus the charge times potential at the end point. Now to solve for V, we have to bring Q final to the other side, so we would have QV initial minus QV final. So that's Q times V initial minus V final, or delta V, the change of potential that we go through. So Q delta V, which is equal to 1/2 mv squared. And now we can rearrange this expression to solve for what the velocity is. And we can find out the velocity just depends on knowing, well, how much charge is there? How much mass is there? We do need to know the mass of the charge because the heavier mass is going to experience more inertia, and therefore it won't be able to speed up quite as much. So that's going to be an important piece. And then also the potential difference that this moves through. That's the key piece. But you can see it's actually a very simple expression. We just need to know mass, charge, and potential difference. We don't even need to know the distances here. The distance comes into play in here because delta V tends to be the electric field times the distance you move through. But again, that's not the perspective we're going to use quite as often. So I just wanted to go through this because these are the types of problems that we're going to be focusing our attention on. It's going to be using conservation of energy to take a look at this picture. There can be some other ways. There may be a problem, 1 or 2 problems that we do here and there, but that's not the key point. This is really what I want to focus our mathematical attention on. In this type of picture where we have a uniform field.